It wasn't a battle they could see. No gunfire echoed across the Rhine valleys, no bombers darkened Berlin's sky in that particular way. Yet by 1944 the German war machine was starving of fuel, of steel, of hope itself. In a captured U-boat report, one Kriegsmarine officer scrawled with trembling precision, "Sie haben alles, wir haben nichts." They have everything, we have nothing. The Americans had transformed factories into weapons of mathematical certainty, cargo ships into vectors of inevitable defeat, and the arithmetic of collapse was already written in production ledgers from Detroit to Pittsburgh. This is the forensic account of how the United States crushed Nazi Germany without ever firing a bullet. A war won not through courage or tactics, but through the cold, relentless logic of industrial capacity. The invisible front, the logistical suffocation, the technological asymmetry so profound that by war's end, German soldiers were scavenging cigarettes from captured ration packs, while American depots burned surplus supplies. By the early months of 1941, Adolf Hitler's territorial empire stretched across 3.9 million square kilometers from the Atlantic coastline at Brest to the forward observation posts outside Moscow, from the Norwegian Arctic Circle to the deserts of North Africa. His Wehrmacht had perfected blitzkrieg doctrine, a tactical synthesis of mechanized infantry, close air support, and wireless coordination that compressed weeks of traditional warfare into days of operational shock. Between September 1939 and June 1941, German forces achieved an average territorial acquisition rate of 47 kilometers per day during active campaigns, a velocity unprecedented in military history. But beneath the newsreel footage of Tiger tanks and Stuka dive bombers, a quieter contest was already unfolding across spreadsheets, railway timetables, and cargo manifests. This was a war that neither tactical brilliance nor individual courage could decisively influence. The ultimate verdict would emerge from the cold mathematics of resource extraction, industrial conversion, efficiency, transportation, network capacity, and supply chain resilience under sustained pressure. Germany's strategic calculations presumed a short war, the kind that could be won through operational speed before structural economic weaknesses became operationally relevant. Hitler's generals had studied the Western Front's attrition catastrophe and designed their doctrine specifically to avoid it. Speed would substitute for depth. Conquest would generate the raw materials that conquest required. The entire system functioned as a perpetual motion machine, provided it never stopped moving. America, by contrast, was preparing for industrial total war, the kind measured not in weeks but in fiscal years, not in kilometers gained, but in production capacity multiplied. When Franklin Roosevelt called for 5,000 aircraft in 1940, military planners considered it rhetorical impossibility. The United States possessed neither the factory floor space, the skilled workforce, nor the machine tool inventory to manufacture such quantities. Yet this impossibility would become the foundational assumption of American strategic planning. This divergence between tactical velocity and industrial depth, between conquest-driven supply and production-driven abundance, contained within it the entire narrative arc of the European theatre. The war's outcome was being determined in corporate boardrooms and factory design studios long before the first American boot touched Normandy sand. In January 1940, the United States Army ranked 18th in global military force, projection capacity smaller than Portugal's standing force, possessing fewer operational tanks than Romania, maintaining an air corps with 1,700 aircraft compared to Germany's 4,200 frontline machines. The American industrial base, still recovering from Depression-era capacity underutilization, operated at approximately 63% of theoretical maximum output. Manufacturing employment had plateaued at 3 million workers, down from the 1,929 peak of 10.7 million. Machine tool production, the critical metric determining how rapidly factories could be retooled for alternative production, stood at 27400 units annually, a figure that would need to multiply by factors of 10 to support sustained armament manufacturing. Then, December 8, 1941, initiated what economic historians would later term the most rapid industrial transformation in recorded history. Within 96 hours of the Pearl Harbor attack, the Automotive Council for War Production had converted design specifications. Ford's River Rouge complex, which had produced 6,900 civilian automobiles in November, began retooling for B-24 Liberator bomber production. The Willow Run facility, constructed on 975 acres of Michigan farmland, beginning March 1941, would eventually achieve a production cadence of one complete four-engine bomber every 63 minutes during peak output periods. In 1944, Henry Kaiser's shipbuilding operation represented industrial transformation through pure methodological innovation. Traditional maritime construction required 355 days from keel laying to commissioning. Kaiser's Richmond Shipyard No. 2, employing prefabrication modularity and continuous flow assembly techniques adapted from automotive manufacturing, reduced this timeline to an average of 42 days by 1943. The Robert E. Peary, launched November 12, 1942, achieved a construction to launch interval of 4 days, 15 hours, 30 minutes, a record that stands as testimony to what organizational theorists call radical process compression, through systematic deconstruction of sequential dependencies. The aggregate production metrics reveal the scope of this mobilization. Between 1,940 and 1,945 American factories manufactured 297,000 aircraft of all types, representing 47% of global wartime aviation production. Tank and self-propelled gun output reached 88410 units, artillery pieces 257,000, small arms 20 million rifles and carbines. Merchant shipping tonnage increased from 1.1 million deadweight tons in 1941 to 19.2 million deadweight tons in 1943, a 1,745% expansion in 24 months. This represented not incremental growth, but exponential scaling of productive capacity through three primary mechanisms: capital investment in new facilities, labor force expansion through previously excluded demographic groups, and technological innovation in manufacturing processes themselves. The workforce transformation merits particular analysis. Female participation in manufacturing increased from 12 million workers in 1940 to 19.4 million by 1944, a demographic shift that permanently altered labor market dynamics. Training programs compressed skilled machinist education from multi-year apprenticeships to 6-week intensive courses, achieving through pedagogical innovation what traditional craft guild structures had resisted for centuries. Average weekly manufacturing wages increased 65% between 1,940 and 1,944, from $25.20 to $41.58 driving consumption capacity, even as rationing constrained civilian goods availability. Yet, beyond the quantitative metrics lay a qualitative transformation in how Americans conceptualized industrial production itself. The assembly line, previously associated with cost reduction and product standardization, became reconceptualized as a tool of national survival. Engineers who had spent careers optimizing refrigerator manufacturing suddenly found themselves calculating bomb payload aerodynamics. The distinction between civilian and military production collapsed entirely. Every factory became a munitions plant, every worker a participant in mechanized warfare's logistical substrate. This was industrial resurrection, not as metaphor, but as technical description, taking dormant capacity, underutilized labor pools, and peacetime engineering expertise, then systematically reorganizing these inputs into a production architecture optimized for a single objective, the generation of material superiority so overwhelming that tactical considerations became progressively irrelevant to strategic outcomes. The calculus of combat logistics reveals warfare's fundamental asymmetry. Every American soldier who crossed the English Channel carried with him a logistical shadow weighing 2.04 tons, the accumulated mass of rations, ammunition, spare parts, medical supplies, and what military planners categorized as morale maintenance items, including cigarettes, writing paper, and recreational equipment. This figure represented not excess but systemic necessity, the minimum material requirement for sustaining operational effectiveness in mechanized warfare's high-consumption environment. Behind each frontline combatant stood a support structure of 16.3 personnel, a ratio that German military theorists initially interpreted as evidence of American inefficiency until they recognized it as evidence of American comprehensiveness. This personnel allocation reflected a doctrinal commitment to logistics-first warfare supply clerks, tracking 4.7 million individual stock-keeping units across 687 standardized categories, transportation specialists maintaining 1-2-4-0-0-0 trucks in the European theater alone, petroleum distribution engineers managing daily fuel consumption rates that exceeded Germany's total monthly synthetic production capacity. The mathematics of Operation Overlord. The Normandy invasion demonstrated this logistical philosophy at maximum expression. The operation mobilized 6939 vessels across 12 different ship classifications, transported 156,000 troops in the initial assault phase, and pre-positioned 104428 vehicles, including 3306 tanks and tank destroyers. The supporting infrastructure included 11590 aircraft, conducting 14674 sorties on D-Day itself, consuming 321,000 gallons of aviation fuel per hour during peak operational periods. Behind this visible armada lay 24 months of preparatory logistics, constructing 163 temporary airfields across southern England, stockpiling 3 million tons of ammunition and equipment, conducting 73 distinct large-scale training exercises to identify and resolve supply chain bottlenecks before operational deployment. German military intelligence observing Allied preparations through aerial reconnaissance and signals intercepts calculated the invasion force's scale with reasonable accuracy. What they failed to comprehend was the sustainability architecture of the systems, ensuring that initial supplies would be followed by continuous resupply at rates matching or exceeding consumption. The Mulberry Harbour's prefabricated port facilities towed across the Channel and assembled off Normandy beaches achieved cargo discharge rates of 11,000 tons daily by mid-July 1944, equivalent to a medium-sized peacetime commercial port's throughput. This represented technological problem-solving at strategic scale, recognizing that German control of deep-water ports would constrain Allied logistics. American and British engineers simply manufactured portable ports and brought them to France. The operational tempo metrics reveal how logistics enabled tactical momentum. By September 1944, American forces, advancing from Normandy toward Germany's western frontier, consumed supplies at a daily rate of 33127 tons, 15240 tons for Third Army alone. The Red Ball express an improvised trucking operation utilizing 5958 vehicles driven primarily by African-American quartermasters' corps personnel, delivered 412,193 tons of supplies over 81 days of continued operation, averaging 5088 tons daily across 686-kilometer round-trip routes. These convoys operated 24-hour schedules, drivers sleeping in shifts while vehicles maintained constant motion, a system that military historians recognize as functionally reinventing freight logistics under operational conditions that would have paralyzed conventional distribution networks. The German General Staff trained in Clausewitzian doctrine, emphasizing maneuver and decisive battle, interpreted logistics as a support function subordinate to tactical excellence. American planners, influenced by industrial management theory and scientific efficiency principles, reconceptualized logistics as the primary strategic instrument with combat operations, serving as the mechanism for consuming pre-positioned material advantages. This philosophical divergence manifested in comparative fuel consumption rates. American forces in Western Europe utilized 11 million gallons of petroleum products daily by autumn 1944. While Germany's entire synthetic fuel production capacity peaked at 316,000 barrels daily, approximately 13.3 million gallons, to supply all Wehrmacht, Luftwaffe and Kriegsmarine operations across multiple theaters simultaneously. The war had become an equation with one variable: who could sustain material consumption at combat-relevant rates. By mid-1944, only one side possessed an answer. The hydrocarbon asymmetry between Axis and Allied powers represented warfare's most fundamental material, imbalance energy availability functioning as the limiting constraint on all mechanized military operations. Germany's 1941 petroleum situation revealed a nation attempting industrial-scale modern warfare while possessing negligible natural crude reserves. Domestic production yielded approximately 4,500 barrels daily, roughly 0.7% of operational requirements. Romanian Ploiești oil fields contributed 3.9 million tons annually, significant, but insufficient for a military apparatus, consuming petroleum at rates exceeding 10 million tons per year during active operations. The Fischer-Tropsch synthetic fuel process, developed in 1925 and industrialized throughout the 1930s, represented Germany's technological solution to geological constraints. This catalytic conversion methodology transformed lignite coal and coke into liquid hydrocarbons through high-temperature, high-pressure chemical reactions. By 1943, Germany operated 23 major hydrogenation plants with combined theoretical capacity of 5.7 million tons annually. Yet this figure masked critical inefficiencies. The energy input required to synthesize 1 barrel of gasoline consumed approximately 4.3 tons of coal, creating a negative energy return ratio when transportation costs and industrial overhead were factored into comprehensive systemic analysis. American petroleum infrastructure, conversely, functioned as geological windfall, combined with technological sophistication. In 1941, United States crude production reached 1.4 billion barrels annually, 60.3% of global output. The Texas-Louisiana Gulf Coast refineries alone possessed greater processing capacity than Germany's entire synthetic fuel network. Standard Oil's Baton Rouge facility could refine 4,230,000 barrels daily, using catalytic cracking techniques that yielded 28% more aviation gasoline per barrel of crude than traditional distillation methods. This represented not merely quantitative advantage, but qualitative technological superiority in the thermodynamic efficiency of hydrocarbon molecular reconfiguration. The operational implications manifested across every dimension of mechanized warfare. A single Panzer IV medium tank consumed 300 liters of fuel per 100 kilometers of cross-country movement, a burn rate requiring continuous logistical replenishment that German supply infrastructure increasingly could not sustain. By Operation Citadel in July 1943, 4th Panzer Army's offensive momentum collapsed, not from tactical defeat but fuel exhaustion. Units achieved initial penetration depths of 35 kilometers before logistical constraints forced operational halts. Field commanders reported tanks abandoned with mechanical functionality intact, but fuel tanks empty crews destroying their own vehicles to prevent capture. Luftwaffe flight training protocols reveal energy scarcity's cascading effects on operational readiness. By 1944, German fighter pilots received an average of 112 flight hours before operational deployment, reduced from the 1,941 standard of 240 hours. Advanced training shifted to glider operations to conserve aviation gasoline-producing pilots technically qualified in aerodynamics, but critically deficient in high-performance aircraft handling under combat stress conditions. This training deficit translated directly to attrition rates. Inexperienced pilots demonstrated kill-to-loss ratios of 1:3:7 versus experienced aviators' 4:2:1 ratios, creating a death spiral where fuel conservation measures accelerated the very attrition patterns they sought to mitigate. Meanwhile, American petroleum logistics achieved industrial-scale fluid dynamics that German planners considered theoretically impossible. The Red Ball Express trucking operation alone consumed 350,000 gallons daily, more than the Luftwaffe's entire Western Front aviation fuel allocation. By December 1944, Allied forces in Western Europe utilized 11.4 million gallons of petroleum products daily across all operational categories: vehicle fuel, aviation, gasoline, diesel for generators, lubricants for weapons, systems heating oil for winterized encampments. This consumption rate exceeded Germany's total synthetic production capacity by factors of 2.81. And this calculation excluded Pacific Theater operations strategic bomber fuel consumption from England-based facilities, and maritime fuel oil for naval vessels. The energy war was decided not through combat attrition, but through thermodynamic inevitability. One side possessed geological abundance amplified by refining technology. The other possessed chemical ingenuity, constrained by physics, and physics indifferent to tactical excellence, authored the mathematical proof of unsustainability. The Liberty ship represented industrial democracy's answer to submarine warfare's geometric problem. U-boats were sinking Allied merchant tonnage at rates exceeding replacement capacity, creating a negative equilibrium where material abundance in North America became operationally irrelevant if it could not cross the Atlantic. In 1942, German submarines achieved a sinking rate of 6.2 million gross register tons, 584 vessels lost, representing transport capacity sufficient to supply 2.3 million troops with full logistical requirements for one operational year. British shipyards operating under bombing conditions and constrained by traditional construction methodologies required 244 days, average build time per vessel, producing approximately 1.3 million tons annually against loss. Rates triple that figure. The EC-2S C-1 emergency cargo ship, officially designated the Liberty ship, emerged from a radical reconceptualization of maritime construction as mass production challenge rather than craft engineering tradition. The design originated from a 1879 British tramp steamer blueprint, deliberately antiquated to prioritize manufacturability over performance characteristics. Specifications included 441 feet length overall, 57-foot beam, 10800 deadweight tons, cargo capacity, reciprocating triple expansion steam engine, generating 2500 horsepower for 11-knot maximum speed. These parameters optimized for single criterion, minimal skilled labor requirements and maximum production velocity through prefabrication modularity. Henry Kaiser's Richmond shipyard revolutionized construction through systematic application of automotive assembly principles to maritime engineering. Traditional ship construction proceeded sequentially: keel laying, frame erection, plate riveting, with each phase dependent on prior completion. Kaiser's methodology decomposed the vessel into 250 prefabricated sections, manufactured simultaneously across distributed facilities, then assembled via welding rather than riveting, reducing labor hours per ton from 1,100 to 470, while eliminating the 12-week training period required for skilled riveters. Welding crews trained in 2-week intensive programs could achieve structural integrity equivalent to riveted joints while working 3 times faster. The production curve demonstrates exponential learning effects under competitive pressure. First, Liberty ship construction, September 1941, required 244 days. By December 1941, average build time had compressed to 105 days. April 1943 marked achievement of steady-state production efficiency. 42-day average construction interval across 7 major shipyard complexes. The Robert E. Peary's 4-day, 15-hour, 30-minute record represented statistical outlier rather than sustainable norm, but demonstrated theoretical minimum achievable through perfect resource coordination, a benchmark that drove continuous process optimization across all facilities. The aggregate production metrics reveal industrial warfare's mathematical inevitability. Between 1941 and 1945, American shipyards launched 2 710 Liberty ships, representing 29.3 million deadweight tons of cargo capacity. Supplementary programs: Victory ships T, 2 tankers escort carriers converted from merchant hulls added 17.4 million tons. Combined Allied shipbuilding output reached 53.7 million tons between 1942 to 1945 versus Axis U-boat sinking totals of 14.8 million tons across the same period. The crossover occurred in November 1943. Monthly construction tonnage permanently exceeded monthly losses, transforming the Battle of the Atlantic from strategic uncertainty into mathematical countdown toward Axis logistics. Collapse. Yet beyond tonnage calculations lay a subtler strategic insight. The Liberty ship program demonstrated that industrial warfare's decisive advantage accrued not to technological sophistication, but to production scalability, married with Operational redundancy. A single Liberty ship possessed inferior performance characteristics compared to purpose-designed cargo vessels, slower, less fuel-efficient, more vulnerable to structural fatigue. But aggregate fleet capacity rendered individual vessel performance irrelevant. Germany could sink ships. America could sink scarcity itself, achieving through mass production what no defensive technology could provide, the transformation of material abundance from geographic fact into operational reality, across 3,000 miles of contested ocean. The submarine war was lost not through convoy tactics or sonar technology, but through shipyard throughput rates that transformed sinking vessels from strategic catastrophe into acceptable attrition within sustainable loss parameters. The caloric dimension of mechanized warfare reveals a constraint as fundamental as petroleum availability, human metabolic requirements functioning as non-negotiable biological constants within military operations. A combat infantryman under field conditions requires 4,500 kilocalories daily to maintain operational effectiveness, 60% above civilian baseline consumption due to physical exertion, thermal regulation in variable climates, and metabolic stress responses under combat conditions. Multiply this individual requirement by 12. 1 million American personnel under arms by 1945, then add Allied force-feeding obligations and civilian population stabilization programs in liberated territories, and the aggregate demand reaches 17.3 million tons of food products annually requiring transoceanic transport, climate-controlled storage and forward distribution networks operating under combat conditions. American agricultural output scaled to meet this requirement through systematic application of industrial farming methodologies developed during the interwar modernization period. Mechanized harvesting equipment, combine harvesters, mechanical corn pickers, industrial threshers increased per acre yield efficiency by factors of 3.71 compared to manual labor methods. Chemical fertilizer application expanding from 2.3 million tons in 1940 to 7.8 million tons by 1945. Enhanced soil productivity through synthetic nitrogen fixation processes derived from ammonia synthesis chemistry, originally developed for explosives manufacturing. This represented technological convergence, the same Haber-Bosch process, generating TNT precursors, simultaneously revolutionized agricultural chemistry, creating food abundance through insights from industrial death. The logistics of food preservation and distribution demanded innovation parallel to weapons manufacturing. Dehydration technologies reduced transport weight by 82%. 1 pound of dehydrated potato flakes reconstituted to 6.3 pounds of consumable product, transforming cargo capacity constraints into multiplicative force. Projection advantages. Canning operations industrialized at unprecedented scale. The Continental Can Company's production increased from 8.4 billion units in 1939 to 43.7 billion units by 1943, requiring construction of 47 new manufacturing facilities and development of automated sealing equipment capable of processing 1,200 cans per minute with failure rates below 0.03%. The German caloric situation, conversely, deteriorated through conquest's inherent contradiction. Territorial expansion increased mouths, requiring feeding faster than it increased agricultural capacity. Wehrmacht rations, designed at 3,000 kilocalories, daily achieved this standard only sporadically after 1943. Frontline units in sustained combat operations reported receiving 1,800 to 2,200 kilocalories daily, sufficient to prevent starvation but inadequate for maintaining physical performance under mechanized warfares. Metabolic demands. Ersatz substitutes proliferated coffee, manufactured from roasted acorns, margarine from coal tar derivatives, protein supplements from pressed soybeans, and industrial yeast cultures. These substitutions maintained minimal nutritional functionality while creating psychological demoralization effects that Wehrmacht morale reports documented with clinical precision. The psychological warfare dimension of food abundance merits analytical consideration. American K-rations included cigarettes, chocolate bars, chewing gum, and toilet paper items with negligible nutritional value, but profound morale implications, signaling an industrial system so abundant it could afford operational Inefficiency for psychological benefit. German prisoners of war processed through Allied detention facilities encountered food service protocols that provided 3,200 kilocalories daily, exceeding their combat rations by 47%. Former Wehrmacht Corporal Heinz Kuhn, interviewed in 1947, recalled his initial response: "They gave us white bread, real coffee, and butter without sawdust." In that moment, I understood intellectually what I had refused to believe. Emotionally, we had lost, not through courage deficit, but through confronting an economic system we could never match. The strategic insight transcended immediate nutritional logistics. American food abundance demonstrated industrial warfare's fundamental asymmetry, where one side fought to survive, while the other possessed surplus capacity. Compassion itself, becoming an instrument of psychological warfare, demonstrating dominance through the luxury of generosity, under conditions where scarcity would be strategically rational. The coordination architecture undergirding American logistics operations represented organizational complexity at scales previously considered theoretically unmanageable without computational automation. By June 1944, the War Department's Services of Supply Division tracked 4.7 million individual stock-keeping units across 687 standardized material categories, maintaining real-time inventory awareness across 126 major supply depots distributed globally from Brisbane to Reykjavik. This informational infrastructure operated entirely through manual data processing clerks, transcribing, shipping manifests, telegraph operators, transmitting requisition codes, statistical analysts reconciling consumption projections against production schedules using mechanical calculators and logarithmic tables. The system functioned as distributed analog computation, where human cognitive capacity substituted for digital processing through radical organizational decomposition and standardized communication protocols. The railroad network scaling reveals infrastructure transformation under compressed timelines. American freight rail capacity in 1940 consisted of two 3000 locomotives hauling 1.7 million freight cars across 233,000 route miles, a system designed for peacetime commercial traffic, moving agricultural commodities and consumer goods at economically optimal speeds. War mobilization demanded throughput increases without proportional infrastructure expansion. Average freight car utilization increased from 12.3 loading cycles annually in 1940 to 23.7 cycles by 1944, achieved through operational tempo acceleration rather than rolling stock multiplication. The Pennsylvania Railroad alone transported 943 million ton-miles of war materials during 1944, equivalent to moving the Empire State Building's mass from New York to San Francisco, 2,847 times within 12 months. Port operations underwent systematic technological revolution through mechanization and process standardization. The Port of New York, handling 37% of East Coast war material shipments, processed 42.3 million tons of cargo in 1944 versus 18.1 million tons in 1940, a 134% throughput increase achieved through innovations, including palletization, reducing cargo handling time per ton from 4.2 hours to 0.7 hours, mechanized cranes increasing lift capacity from 8 tons to 37 tons per unit, and standardized cargo containerization protocols, enabling intermodal transfer efficiencies that prefigured the containerization revolution of the 1,960 seconds by 20 years. The personnel mobilization dimension reveals total societal integration into logistical infrastructure. By 1944-30, 1 million Americans worked directly in war-related industries, representing 55% of the total labor force. This figure excluded the 12.1 million in military service, creating combined war effort participation of 42.2 million from a total population of 138.4 million, 30.6% of the entire population actively engaged in material production or military operations. Demographic groups previously excluded from industrial employment: women, African Americans, disabled individuals, workers over age 55, entered manufacturing sectors at unprecedented rates, expanding the effective labor pool beyond pre-war. economic models' theoretical maximums. The precision achieved within this massive system defied conventional organizational theory. Supply requisitions filed from forward combat units in France reached fulfillment in average timeframes of 7 days from requisition submission to material delivery at battalion-level supply points, a performance metric requiring coordination across oceanic shipping, rail transport depot, warehousing, and tactical distribution networks, all operating under combat conditions with active interdiction threats. The error rate for critical spare parts delivery items where specification mismatches rendered components operationally useless measured to 3%, a figure comparable to modern just-in-time manufacturing tolerances achieved with computerized inventory management systems. German military logistics, by contrast, operated through organizational structures optimized for pre-mechanized warfare's lower throughput requirements. The Wehrmacht supply system utilized 2-4-3-7 distinct vehicle types, requiring non-interchangeable spare parts, creating inventory complexity that overwhelmed manual tracking capabilities. American forces standardized on 467 vehicle types, with 73% parts commonality across similar weight classes, transforming logistics from artisanal craft into industrial process, a conceptual transformation as decisive as any. Tactical innovation. The front line wasn't in Europe. It was distributed across every factory floor, railroad yard, and shipping manifest where anonymous administrators transformed chaos into coordination. By September 1944, the German war economy exhibited characteristics of systemic collapse, not through sudden catastrophic failure, but through progressive degradation across multiple interdependent subsystems simultaneously. Overwhelming compensatory mechanisms. The Reichsministerium für Rüstung und Kriegsproduktion documented aircraft production declining from peak monthly output of 353 art units in July 1944 to 1,104 units by March 1944, a 60%, contraction within 8 months. Yet raw production figures masked more fundamental dysfunction, fuel scarcity, grounded 47% of manufactured aircraft immediately upon factory completion, transforming them from operational assets into immobile inventory consuming hangar space without contributing to combat capability. The petroleum crisis achieved terminal phase during autumn 1944, when sustained Allied strategic bombing eliminated synthetic fuel production capacity faster than repair crews could restore functionality. The Lohner Hydrogenation Complex, Germany's largest synthetic fuel facility with theoretical capacity of 350,000 tons, annually suffered 22 separate bombing attacks between May and December, 1,944, reducing actual output to 9% of design capacity. By January 1945, total German fuel production measured 23,000 tons, monthly sufficient to support approximately 340 operational sorties by the entire Luftwaffe fighter force or fuel, 1,200 tanks for 100 kilometers of movement. These figures represented strategic impossibility, maintaining defensive operations across collapsing fronts, while allocating fuel reserves insufficient for either air defense or armored counterattacks. The transportation infrastructure disintegration accelerated through recursive failure cascades. Allied air interdiction destroyed 9827 locomotives and 138000 freight cars between January-December 1944, while simultaneously cratering 2847 railway bridges and severing main trunk lines at 14332 distinct points. Repair capacity dependent on the same transportation network requiring restoration could not match destruction rates, creating negative feedback loops, where each unrepaired rail segment increased pressure on surviving routes, accelerating their operational degradation through overutilization stress. By March 1945, German rail freight capacity operated at 11% of 1,944 levels, effectively severing industrial regions from frontline forces and rendering centralized logistics coordination functionally impossible. Wehrmacht mechanization reverted to pre-industrial methodologies through material necessity rather than doctrinal choice. Fourth, Panzer Armies December, 1,944 equipment inventories, documented 4,847 horses pressed into freight service, exceeding operational tank inventory by ratio of 3:1. Armored divisions, theoretically mobile exploitation forces, operated as static defensive positions due to fuel unavailability, transforming doctrine through supply constraint rather than tactical reconsideration. Field commanders reported cannibalizing disabled vehicles for functional components, creating ersatz hybrid machines, combining engines from one chassis with transmissions from another mechanical Frankensteins, demonstrating engineering desperation unthinkable within armies possessing intact supply chains. The comparative consumption asymmetry by late 1944 revealed economic warfare's mathematical conclusion. American forces advancing toward the Rhine consumed materiel at daily rates exceeding Germany's total monthly industrial output across multiple categories. Simultaneously, 3312, 7 tons of general supplies versus German production capacity of 28,000 tons monthly. 11 million gallons of petroleum products versus 9.7 million gallons total German availability. 197,000 artillery rounds expended versus 134,000 rounds manufactured. The Wehrmacht was fighting not merely an enemy army, but confronting an economic system capable of sustaining consumption rates that exceeded Axis production capacity, even when that production operated without interdiction or supply constraints. The Reich's collapse proceeded as thermodynamic inevitability entropy increasing within a closed system, unable to import sufficient energy to maintain organizational coherence. Tanks rusted in factory yards awaiting fuel that would never arrive. Soldiers consumed rations calculated for retreat velocities their transportation capacity could no longer achieve. The mathematical equation of industrial warfare had reached its terminal proof. Courage and tactical skill could delay, but not reverse outcomes already determined by production ledgers written 3 years prior. The definitive interpretation of Germany's defeat requires acknowledging an uncomfortable historical truth. The outcome was determined not through decisive battles or tactical genius, but through industrial mathematics operating at scales beyond traditional military comprehension. The atomic weapons deployed at Hiroshima and Nagasaki represented technological culmination, yet their strategic impact paled against the cumulative effect of 2710. Liberty ships 297,000, aircraft and logistics networks, moving 33,000 tons daily across contested geography. American victory emerged from systematic reconceptualization of warfare itself, transforming combat from Clausewitzian decisive engagement into extended industrial consumption contest, where material abundance functioned as the prime strategic instrument. For every explosion registered on frontline combat reports, 1,000 invisible logistical transactions occurred in rear echelons. Requisition forms, processed cargo manifests, reconciled fuel allocations, calculated spare parts, inventoried. This administrative apparatus, unglamorous and numerically dense, constituted the actual mechanism of strategic defeat. German military theorists termed this phenomenon Materialschlacht, the battle of materials, invoking the concept with undertones of contempt, as though industrial capacity represented unfair advantage, negating tactical virtuosity. American planners conceptualized it differently, as applied systems engineering, where victory emerged from optimizing production functions, minimizing supply chain latencies, and achieving logistical throughput rates sufficient to sustain operational tempo indefinitely. The war's historiography traditionally emphasizes combat narratives, beaches, stormed cities, liberated armored breakthroughs. Yet the decisive front existed in Detroit. Assembly plants, Richmond shipyards, and Pennsylvania Railroad coordination centers, where anonymous personnel transformed industrial potential into operational reality. They were soldiers in a different uniform, fighting battles measured in production quotas rather than territorial gains, winning through spreadsheets what others pursued through sacrifice. Wars embed themselves in collective memory through combat narratives, beaches stormed under fire, armor clashing across open plains, aircraft dueling at altitude. The historical imagination gravitates toward kinetic drama, toward moments where individual courage confronts mortality. Yet the most consequential victories often occur in spaces absent from heroic narrative accounting offices, calculating depreciation schedules, transportation coordinators, optimizing rail routing algorithms, industrial engineers redesign factory floor layouts for throughput maximization. The men and women who welded hull plates at Richmond shipyards, who inventoried spare parts in Quartermaster Corps depots, who reconciled shipping manifests across transatlantic supply chains, they too prosecuted warfare, albeit through different instruments. Their battlefield was organizational complexity, their weapon was systematic coordination applied at industrial scale. In warfare's final accounting, tactical brilliance proves ephemeral against logistical inevitability. Individual battles determine daily headlines. Industrial capacity determines historical outcomes. The mathematics remain unambiguous. Wars transform individual lives through violence, but logistics transforms civilization through capacity. The quiet, relentless accumulation of material advantage that renders courage insufficient and tactics irrelevant. As Roosevelt articulated with characteristic precision, we must be the great arsenal of democracy. History proved him literally devastatingly correct.